So this is section 6.6, which is about solving exponential and logarithmic equations. We're going to look at a bunch of different types of logarithmic equations and talk about different strategies that we can use to solve them. The first type is actually something we saw back in 6.3 when we first started talking about exponential functions. If you have an exponential equation where you can rewrite them with the same base, where they can both have base b, then you are allowed to take the exponents and set them equal to each other. And so the kind of steps we follow with these ones is, first off, rewrite the equation so that both sides have the same base, then set the exponents equal to each other, and then solve for the variable. And if you can do this, you want to do it because those equations are usually pretty easy to solve. So let's look at some examples of this. Our first one, we have 2 raised to the 3x minus 8 power equals 16. Is there a common base for 2 and 16? Yeah, there is. The base is 2. So we're going to leave this first one as 2 raised to the 3x minus 8. And we're going to rewrite 16 as 2 to the 4th power. Now that they have the same base, we can set the exponents equal to each other. So 3x minus 8 equals 4. Add the 8 across, so 3x equals 12. And then divide both sides by 3, and we get x equals 4. Okay. Example B, we have 27 raised to the x plus 3 power equals 9 raised to the x minus 1 power. Is there a common base between 27 and 9? Yeah, they're both powers of 3, so they can be rewritten. So 27 is 3 to the 3rd power, and it's getting raised to the x plus 3. And 9 is 3 to the 2nd power, and it's getting raised to the x minus 1. Now here you do have to simplify a little bit using your exponent rules. You have a power raised to a power, so you're going to multiply the exponents. So this one's going to become 3 raised to the 3x plus 9 power. And this one's going to become 3 raised to the 2x minus 2 power. Now that they have the same base, we can set the exponents equal to each other. So 3x plus 9 equals 2x minus 2. Let's subtract the 2x across first. So 3x minus 2x is x. So x plus 9 equals negative 2. Then we can subtract 9, and we get x equals negative 11. So that's how those ones work. And again, if you can rewrite them with the same base, do it, because these equations are usually not too hard to solve. They're actually much easier than some of the other equations we might look at. So I would highly recommend doing that. Alright, so what if we can't get a common base? Well, when we can't get a common base, we usually use logarithms to help us solve. So the steps we follow when we can't get a common base look like this. Step 1, isolate the exponential expression. Get the exponential by itself. Step 2, take a common log or a natural log on both sides. Here I say only do common log if the base is 10, but you can technically do either one anytime. I usually favor natural logs, but you can technically do either one, a natural log or a common log, in any of these problems, and it will still work out. It's just sometimes common log is more convenient, sometimes natural log is more convenient. Once you've taken a logarithm on both sides, the third step is to use your properties of, and this should say logarithms, not exponents. So remember from 6.5 that if you have a power inside of a logarithm, you can move the power to the front, like this. Remember that an ln and an e cancel each other out. And also remember that a log and a base 10 also cancel each other out. Once you've done that, then you can solve the remaining equation for the variable and get your answer. So let's look at some examples of this. Example 2a, we have 4 raised to the x power equals 15. Is there a common base for 4 and 15? No. So we're going to try and solve this with logarithms. we isolate the exponential, which in this case it's already isolated. So then we're going to take a log on both sides. So log of 4x equals log of 15. Then we'll use our properties of logarithms, and we will move the variable, the exponent, to the front. So we'll have x equals log 4. Sorry, not x equals, x times log 4 equals log 15. And then we can divide both sides by log 4. So our exact answer is log 15 over log 4. But we can also give a decimal approximate if we go to our calculator. So log of 15 divided by log of 4. That comes out as 1.953. So that's our approximate answer. All right. Letter B, we got 10 raised to the x equals 120,000. There is not a common base between 10 and 120,000, so we can't use that method. So we isolate the exponential, which it already is isolated. Then we're going to take a log on both sides. So log of 10 raised to the x equals log of 120,000. Now here's the thing. Remember, with your properties, this log has a base 10, this exponential has a base 10. So those can actually cancel, and so we just get x equals log of 120,000. Or, if we want to go to a decimal approximate, let's see, log of 120,000, 5.079. Okay. Let's look at a slightly more difficult one. Not too bad, but a little more difficult. Example 3 asks us to solve 40e to the 0.6x minus 3 equals 237. Now, right away, the exponential is not isolated, so we need to isolate it. So we'll start by adding 3 across. So 40e to the 0.6x equals, if we add 3, 237 plus 3 gives us 240. Then we would divide both sides by 40. So e to the 0.6x equals 240 over 40. Let's see, the zeros could cancel, so it's really just 24 over 4, which is 6. Alright, so now we've isolated it. Compare the bases. We have e and 6. Is there a common base between e and 6? No, there's not. So we're going to use our other strategy, and we're going to use logarithms. Now this time, because this is an e, the logarithm I'm going to use is an ln. So I'm going to do ln of 0.6x equals ln of 6. Now the reason I do that is because an ln and an e will cancel out, and so I'll just have 0.6x equals ln of 6. And then I can solve for x by dividing the 0.6 across. So our exact answer is ln of 6 divided by 0.6. Or we can go to an approximate and say, okay, we have ln of 6 and dividing it by 0.6. And that's 2.986. 986, yeah, 986. And so that would be our exact answer. Okay, so that was a little bit more complicated. We had to do a little bit of manipulation at the beginning, but not too bad. All right. Example 4 is the one that students usually don't like, just because of how messy it ends up looking. So I will apologize if you don't like this one, but it is what it is. Alright, so we have 5 raised to the x minus 2 equals 4 raised to the 2x plus 3. We already have exponential functions that are isolated. Now, is there a common base between 5 and 4? No. So since there's not, we're going to use logarithms. So we're going to write log of 5 raised to the x minus 2 equals log of 4 raised to the 2x plus 3. Now that we've taken a logarithm on each side, we can use the properties of logarithms to move the exponents to the front. So we have x minus 2 times log of 5 equals 2x plus 3 times the log of 4. Make sure to put the exponent stuff in parentheses because you want to make sure that whole thing gets multiplied by the logarithm. So make sure the parentheses are there like I have written here. Right. The next step is to distribute the logarithm in. So log of 5 times x is x log of 5. Log of 5 times negative 2 is negative 2 log of 5. Over here, log of 4 times 2x is 2x log of 4. And log of 4 times 3 is 3 log of 4. Now, if you look at this equation, you look at how many x's you have. You have an x over here and you have an x over here. In order to solve equations, the x's have to be together. So this 2x log 4, it's going to have to move over here with the x log 5. Similarly, this negative 2 log 5 that doesn't have an x, it needs to move over here to be with the other log that doesn't have an x. So when we do this rearranging, on the left-hand side, we're still going to have x log 5, but we're going to move over this 2x log 4, so we're going to subtract it. So it'll be minus 2x log 4 equals. On the right-hand side, I still have the 3 log 4, but I've moved over this 2 log 5. And so since it was a negative, when I move it over, I'm going to add. So it's going to be plus 2 log 5. At this point, once you've separated the x's and put them on the same side, if you look, both of these terms that are on the left-hand side both have x in them. If something is in common between two things, we can factor it out. So I can actually factor an x out. Now, when I pull it out of this first term, it leaves behind the log 5. Minus, when I pull the x out of this term, it's going to leave behind that 2, and it's going to leave behind that log 4. And then the last step to solve, right now we have x getting multiplied by this parentheses. Well, in order to get the x by itself, to get rid of multiplication, we divide. So we're going to divide both sides by that parentheses, by that log 5 minus 2 log 4. So my exact answer is x equals 3 log 4 plus 2 log 5 over log 5 minus 2 log 4. But we can also get an approximate, and this is where it gets kind of tough because to do these approximates, you're going to have to use a lot of parentheses. So I'm going to open up parentheses for the top of the fraction. And on top I have 3 log of 4, close the log, plus 2 log of 5, close the log, and then close the top of the fraction, divided by, open up a parentheses for the bottom of the fraction, log 5, close the log, minus 2 log 4, close the log, close the bottom of the fraction. And so there's our decimal approximate, negative 6.343. 343. Okay. So you do have to be a little careful putting these in the calculator when you do them. Okay? All right. Example 5. Example 5 asks us to solve e to the 2x minus 4e to the x plus 3 equals 0. Hint, use a substitution so that you can factor. And to this point I want to point something out to you. When you have e to the x and you square it, that's technically a power getting raised to a power. So when you have powers raised to power, you multiply the powers. So this is the same thing as e raised to the 2x power. Now you can also read that backwards. E to the 2x power is actually just e to the x getting squared. And I point that out here because in this equation we do have an e to the 2x. So I could actually just write this as e to the x getting squared minus 4e to the x plus 3 equals 0. And then what I'm going to do over here is I'm going to say, hey, let's pick a variable. Let's say let a equal e to the x. So any place I see an e to the x, I'm going to replace it with a. So here I have e to the x getting squared, so that's really a getting squared, minus 4, and here I have e to the x, so that's really a, plus 3 equals 0. And now you've turned something that may or may not look factorable to you into something that should definitely look factorable to you. So let's factor it. In order to make a squared, I need a times a. In order to make a 3, I need 1 times 3. And in order for it to be a negative 4 in the middle, this will have to be a negative 1 and a negative 3. And we can set those factors equal to 0. And we can solve. And so we get a equals 1 and a equals 3. Now here's the thing though. We didn't start with a. What did we start with? Well, if we look over here, a was actually e to the x. So what we really have is e to the x equals 1 and e to the x equals 3. And so we need to solve those equations. So I'm just going to rewrite them up here. E to the x equals 1, e to the x equals 3. Now these are exponential equations for both of them. Now in this one we do not have a common base, so we can't use the common base method. So instead we're going to take a logarithm. Since this is an e, I'm going to use an ln. So ln of e to the x equals ln of 1. On the left-hand side, the ln and the e can cancel out, and I just get an x. On the right-hand side, ln of 1 is 0. If you remember your properties of logarithms, if you ever put a 1 inside of a logarithm, it's going to give you an answer of 0. And if you don't believe me, go into your calculator, ln of 1 comes out of 0. Okay? All right. For our other one, we have e to the x equals 3. There's not a common base for e and 3, so we're going to have to use logs. And since this is an e, we will use natural logs. So ln of e to the x equals ln of 3. On the left-hand side, the ln and the e cancel out, so we just have x equals. And here we have ln of 3, which we could approximate using a calculator. So ln of 3, 1.099. So ln of 3 would be the exact answer. 1.099 would be the approximate answer. And so that's how we would handle a problem like that. Alright. Next types of equations we're going to look at are equations that involve logarithms. If an equation involves logarithms where you have just a single logarithm and some kind of constant, then what you're going to want to do is use these steps right here. First off, rewrite the equation so that you have a logarithm on one side and your constant on the other side. And note this step might involve condensing the logarithm using the properties of logarithms that we learned about in 6.5. Once you've done that, then in step 2, you are going to rewrite the logarithm as an exponential function. Just like we did in 6.4, you're going to take your logarithm and just rewrite it as an exponential. Step 3, you will solve that equation for the variable and figure out what your variable equals. And then step 4, and this is really important, because you are dealing with logarithms, you have to check your answers in the original equation. Remember that the inside of a logarithm has to be positive, and so you have to check your answers and make sure that they give a positive inside the logarithm when you plug them in. Alright, so let's look at some examples of this. In example 6, it asks us to solve, and here we have log base 4 of x plus 3 equals 2. The logarithm is by itself, and the constant is over here, so that's good. We're fine on that. So we're going to now rewrite this as an exponential. The base is 4, the exponent is 2, and it equals x plus 3. 4 squared is 16, so 16 equals x plus 3. Subtract the 3 across, x equals 13. Now, before I box that answer in, I want to check it. If I plug it back in, 13 plus 3 is 16. That's a positive number, so that's okay. So 13 is fine as an answer. Letter B, we have 3 ln of 2x equals 12. Now, this one's not ready yet to change because I still have this number in front. So the first thing I'm going to do is I'm going to divide both sides by 3. So I'll say ln of 2x equals 12 divided by 3, which is 4. And now I've got it so I just have a logarithm on the left and a constant on the right. So now I will rewrite it as an exponential. The base of my logarithm is e. It's raised to the 4th power, and it equals 2x. And then I can solve for x by dividing both sides by 2. So my exact answer is e to the 4th power over 2. Or I can go for an approximate. So to do my e, I do second ln, and it's what, e to the 4th over 2. So e to the 4th, close the power, divided by 2. So that's 27.299. So that would be our approximate answer for that problem. Okay. Let's look at example 7. Example 7 asks us to solve log base 2 of x plus log base 2 of x minus 7 equals 3. On this one, we have a constant on the right, but we have 2 logarithms on the left. So our first thing that we're going to want to do is condense those logarithms. Now, because we have addition, we can actually rewrite this as one logarithm that has multiplication in it. So this would be log base 2 of x times x minus 7 equals 3. So we just change that addition of 2 logs into a multiplication inside of 1 log. And then we can actually do out that multiplication. So x times x is x squared. X times negative 7 is negative 7x. At this point, we now have 1 logarithm on the left. We have a constant on the right. So we are ready to rewrite this as an exponential equation. Our base is 2. Our exponent is 3. And it equals x squared minus 7x. Now 2 to the 3rd is 8. So we really have 8 equals x squared minus 7x. Since there are x squareds and x's in this equation, we would like to make it equal 0 so that we can factor or use the quadratic formula. So we need to take this 8 and move it over. So 0 equals x squared minus 7x minus 8. And that will factor. To make x squared, I need x times x To make an 8, I could have either 2 times 4 or 1 times 8. For it to be a negative 7 in the middle, it's going to have to be 1 times 8, with the 8 being negative and the 1 being positive. So then we can take those answers, those factors, and set them equal to 0. And so we end up with x equals negative 1 and x equals positive 8. Now again, remember, you got to check your answers with logs. So if we take negative 1 and plug in, immediately we have a problem. This would be a negative inside here, so it will not work. So that answer just doesn't work. For 8, if we take it and check it, 8 when you plug it in here is fine. And over here, 8 minus 7 is 1. 1's positive, so that's fine. So 8 will actually work. 8 will be okay as a solution. Alright, so those are logarithm problems where we have to rewrite them as an exponential. But that's not all types of logarithmic equations. There is another situation you might encounter where you have a logarithm on both sides of the equation. One on the left and one on the right. Well, if that's true, then all you have to do is condense it so that you just have a logarithm on the left and a logarithm on the right. And then take the stuff that's inside the logarithm, in this case the m and the n, and set it equal to each other. And then once you do that, you can solve that equation. And then lastly, check your solutions. Make sure that they do work inside of the logarithms. So let's look at an example of that. So in example 8 here, we're asked to solve ln of x plus 2 minus ln of 4x plus 3 equals ln of 1 over x. I do have ln's on both sides. Before I can set the stuff equal to each other, though, I need to condense these two. This is a subtraction, and subtraction can be condensed into division. So we could rewrite this as ln of x plus 2 over 4x plus 3 equals ln of 1 over x. And then at that point, if this is equal to this, so at this point, we have just one logarithm on each side. So we can actually just set the stuff inside the logarithms equal. So we can say x plus 2 over 4x plus 3 equals 1 over x. And then I want to solve that equation. The first thing I'm going to do is I'm going to multiply both sides by 4x plus 3. Over here and over here. On the left-hand side, the 4x plus 3's can cancel, and so I just have x plus 2. On the right-hand side, when I multiply, I'll end up with 4x plus 3 over x. And then what I'm going to do is I'm going to multiply both sides by x. So here on the right-hand side, the x's can cancel. And so I just have 4x plus 3. On the right-hand side, x times x is x squared. X times 2 is 2x. Now because there are x squareds and x's in this equation, I want everything on one side so that it's equal to 0. So I need to move these terms over. So I have x squared. I take the 4x over. 2x minus 4x is negative 2x. And then I move the 3 over, so I have a negative 3 equals 0. That will factor. To make an x squared, I need x times x. To make a 3, I need 1 times 3. And to make it a negative 2, the 3 has to be negative and the 1 has to be positive. So then we set the factors equal to 0, and we solve. So we get x equals negative 1 and x equals 3. Now you would want to check those answers. So if we take negative 1 and plug in, negative 1 plus 2, that's positive 1, so that's okay. 4 times negative 1 is negative 4, plus 3 is negative 1. That's not okay. So That's a negative number that would be there, so that doesn't work. Let's check 3. 3 plus 2, that's 5, that's okay. 4 times 3 is 12, plus 3 is 15, that's fine. And 1 over 3 is 1/3, and that's fine. So 3 works in all of them, so 3 would be our answer there. Okay. So again, that's another method, another way of solving some of these logarithmic equations. Okay. Another strategy we have for solving these equations is to solve them by graphing. You can use a graphing utility, a graphing calculator, to help you solve some of these equations. So example 9 here, we're going to show how this works. It asks us to solve x plus e to the x equals 2 using a graphing utility and to round your answer to 2 decimal places. Well, what we're going to do is we're going to treat this as 2 separate equations, y1 and y2. So what I have is y1 is the equation x plus e to the x, what's on the left-hand side of the equal sign. And y2 is just the number 2, just the stuff that's on the right-hand side. Okay. And so then we're going to go to our graphing calculator. So here's mine. I'm going to go to y equals, where I can put in equations to graph. And so in y1, I'm going to put x plus e to the x. And then in y2, I'm just going to put the number 2. Before I hit graph, I am going to hit the zoom button and do zoom standard, which is number 6 here, just so my window is the default one. And so here, that first graph is the e to the x graph. And then the horizontal line that gets drawn across here that's the line for 2. And you can see there is a spot where they intersect. There is a spot where they are equal. So we want to find that spot. And with our calculator, we can actually do that. This one, it calls it the intersect function. You hit second trace, and then on this list, number 5 is intersect. It'll ask you for first curve. You hit enter. It'll ask you for second curve. Hit enter. And it'll ask for guess, and you can use your arrows to move it to where you think they cross, and then hit enter a third time, and that'll tell you. There's your intersection point. There's what x has to equal. So x equals, it asks us to round this to 2 decimals, so it's going to be 0.44. So 0.44 is the spot where these 2 equations are equal, which means this equation would be true. Okay? And so that's another way to solve it if you have access to a graphing utility. The very last thing we're going to look at is an application problem. Okay. So example 10 is kind of a preview of what you'll see in 6.7 and 6.8. And so it basically tells us that the formula A equals P times 1 plus R over N raised to the NT power describes the accumulated value A of a sum of money starting with the principal P after T years at an annual percentage rate R, written in decimal form, compounded N times a year. How long will it take $25,000 to grow to $500,000 at 9% annual interest compounded monthly? So first off, we just kind of want to identify what we have. So they told us A is accumulated, P is principal, which is your starting amount, R is your interest rate as a decimal, the N on the bottom and the N up here in the exponent are both how many times per year it's compounded, and then T is time in years. So those are what our variables are. Let's see what they actually gave us. The question says, how long will it take $25,000 to grow to $500,000 at 9% annual compounded monthly? So our first thing is $25,000. What is that? Well, that's our P. That's our principal. It's what we start with. Okay, $50,000. Well, that's our accumulated amount, so that's our A. 9%, that's our interest rate. If we write it as a decimal, it is 0.09 for our R. And then when they tell us compounded monthly, how many months are in a year? Well, there are 12, so we know that N has to equal 12, because it's compounded N times per year, And compounded monthly means every month, so there are 12 months in a year, n equals 12. So we just take all of this stuff and we fill it into our equation. So for A, we have 500,000. For P, we have 25,000. And we have 1 plus. For R, we have 0.09 over. For N, we have 12. Close the parentheses. Up here in the exponent, we have another N, which means we have 12 again. And then we have T, which we don't know. So T is our missing variable. And that makes sense because it asks us how long, which would be time, which is T. So here's our equation. We want to solve this for T. Now this is an exponential equation. So the first thing we're going to do is isolate the exponential. So I'm going to do that by dividing both sides of the equation by 25,000. So if we go to my calculator, so I can quit, I'm going to do 500,000 divided by 25,000. I get 20. So 20 equals, and then I'd also like to figure out what number is in this parentheses. So I'm going to use my calculator. I'm going to do 1 plus 0.09 over 12. And so that's 1.0075. And that gets raised to the 12t power. Okay. So we've cleaned it up a little bit. We've isolated the exponential. The exponential expression is by itself. Now, is there a common base between 20 and 1.0075? No, unfortunately. So we can't use that method. So instead, we're going to use logarithms. So I'm going to take a logarithm on both sides. So log of 20 equals log of 1.0075 raised to the 12t. Now that I've taken a logarithm, I can move the exponent to the front using my properties of logarithms. So log of 20 equals 12t log of 1.0075. Now, these three things are being multiplied. We have a 12 times a t times a log of 1.0075. If we want to solve for t, we need to get rid of this multiplication, so we're going to use division. So we're going to divide both sides by a 12 to cancel that out, but we're also going to divide both sides by the log of 1.0075. So we're going to do that on both sides. And so we'll end up with t equals, and then we just want to use our calculator and figure out what this is. So I have a log of 20, and then I'm dividing that by parentheses 12 log of 1.0075. And so there's my answer, 33.411. And they told us here the time t is measured in years, so that would be my unit on this problem. So it takes approximately 33.411 years for the $25,000 to grow to $500,000. And that is it for 6.6 notes. As always, feel free to email me if you have any problems on the homework or anything.